Do you know how to pronounce meringue?
Meringues.
Okay, thanks. This is a meringue. It's a cookie made out of a mixture of egg whites, sugar, and an acid. You whip up that mixture like this until it's triple in size, and then you bake it. What's really unique about this cookie, though, is its consistency. When you bite into it, you'll see all these air bubbles that's inside the cookie. But what allows this to even happen? What's the science behind this? What molecular interactions allow this consistency to even exist? I'm gonna find that out.
Not all meringues are the same. There's 3 types of meringues: French, Swiss, and Italian. French meringue is the most basic type. All of them essentially have the same ingredients, but involve heat at different phases of the baking process, resulting in different properties of the meringues that make them appropriate for different desserts. There's 2 major parts to the process of baking a meringue. The first is making the foamy mixture, and the second part is baking it. Bakers call this mixture the batter, while scientists call it the continuous phase. The objective of the baker in making the batter is to make it as fluffy as possible, so the cookie ends up having the most volume possible and melts in your mouth. The scientist's objective is to find the answer to this question: what factor contributes to the maximization of the volume and stability of the continuous phase? You probably know this, but just to review, egg whites are basically nature's protein shakes. Its composition is 10.9% protein and the rest is mostly water. When egg whites are whipped, the whisk disturbs the fluid and forces the proteins to trap the water and air within themselves, leading to the emergence of the foamy texture. According to food biophysicists, there's largely 2 things that turn goopy egg whites into fluffy meringue batter: sugars and acids. The sugar is important in reducing liquid drainage of the continuous phase, which means the batter is able to hold its bubbles in for longer and maintain better stability. The sugars have favorable interactions with proteins that allow the proteins to essentially be nicer to each other when they're doing circle time. This makes the bubbles more stable and therefore also stabilizes the continuous phase in the macro scale. The acids also make the batter more stable, but for a different reason. In addition to particulate protein interactions, the egg whites also start to denature and tangle up with one another when they get whipped. Proteins are made of a chain of amino acids called polypeptides, and when they're in unfavorable pHs and/or higher temperatures, they lose their functional shape and turn into biomolecular noodles. This introduces the complication of what bakers call overwhipping, which is when you whip your egg so much that it gets unfluffy. This happens when the proteins tangle up so much that they form a labor union and stages an uprising against the whisk by literally balling up and losing its sweet, sweet fluff. Overwhipping is a baker's worst nightmare, so bakers on YouTube always issued a warning that meringue batter should be whipped for only a certain amount of time. But limiting whipping time isn't the only way to avoid overwhipping. The addition of acids also help prevent proteins from tangling up too much, especially by delaying the formation of disulfide bonds. Disulfide bonds are sulfur-to-sulfur bonds that can be formed between 2 cysteine groups in a protein or 2 proteins to pin parts of the chain together. Unlike hydrogen bonds, disulfide bonds are covalent, so once they form, it's pretty hard to untangle this kind of molecular knot. There are several different enzymes that different species use to form disulfide bonds for their cellular proteins, but the basic mechanism of the chemical reaction is the same across the tree of life. The laboratory method of synthesizing disulfide bonds illustrates the general mechanism quite neatly. The disulfide bridge is formed through a substitution reaction in which the hydrogen on a sulfur attached to one R group is replaced by another sulfur attached to a second R group. First, a base such as bicarbonate takes off the hydrogen through an acid-base reaction, leaving the sulfur with a net negative charge. This leads the sulfur to form a bond with bromine. Since bromine is a good leaving group, a substitution reaction is favored, and another deprotonated sulfide replaces the bromine, forming a disulfide bridge. In the context of proteins, 2 cysteine groups are able to form a disulfide bridge through a very similar reaction mechanism, commonly aided by an enzyme. Adding an acid to the batter interferes with this reaction mechanism and prevents the proteins from chemically tangling up with one another. Once the batter is complete and peaks, the meringue is ready to be baked. In the oven, the water evaporates out of the mixture, and what's left behind are the sugars and proteins. So that's basically everything you never wanted to know about meringues. If you like this video, make sure to subscribe and ring that notification bell so you don't miss another video from me. Bye!